Every morning, before you even step outside, before you decide what to wear, and before pilots take off, farmers water their crops, or ships begin crossing oceans, someone already has an idea of what the sky will do. Rain, storms, heat waves, snow. Somehow this information is known in advance. Yet the strange thing is that no single country controls this knowledge. Instead, hidden across the planet is a quiet global network made up of thousands of machines, floating sensors, orbiting satellites, and powerful computers working day and night. Together, they are constantly trying to answer one question: what will the sky do next? Without this invisible system, modern civilization would be almost blind to the atmosphere's behavior. For most of human history, weather was unpredictable and mysterious. People tried to read the sky by observing clouds, watching birds, or feeling the wind. Sometimes those observations worked, but often they failed. Crops could be destroyed by unexpected frost, ships could vanish into storms, and cities could face floods with almost no warning. A tragic example occurred during the Galveston Hurricane of 1900, when a powerful hurricane struck Galveston and killed more than 8,000 people. At the time, meteorologists had almost no warning because weather forecasting relied on scattered instruments and handwritten reports. Scientists gradually realized something important. Weather is not local. A storm forming over the Atlantic can affect Europe days later. Cold air from the Arctic can travel thousands of kilometers south. In other words, the atmosphere behaves like a massive global machine. Predicting it requires observing the entire planet, not just one region. This realization led to the creation of a planet-wide observation network that now spans mountains, deserts, oceans, and even space. Across the world today, more than 10,000 ground-based weather stations constantly measure atmospheric conditions. These stations record temperature, humidity, air pressure, wind speed, and rainfall, sending their measurements into the global network every few minutes. But ground stations alone cannot capture the full picture of the atmosphere. Twice a day, meteorologists launch thousands of weather balloons carrying small instrument packages known as radiosondes. As the balloons rise through the sky, sometimes reaching altitudes above 30 kilometers, they measure atmospheric conditions layer by layer, recording temperature, wind direction, humidity, and pressure before eventually bursting high in the atmosphere. The oceans, which cover more than 70% of Earth's surface, are also critical to understanding weather. Scattered across the seas are thousands of robotic sensors known as Argo program floats. These devices dive deep underwater, sometimes nearly 2 kilometers below the surface, measuring temperature and salinity as they slowly rise back upward. Every 10 days they surface, transmit their data to satellites, and then descend again. This information is vital because oceans store enormous amounts of heat, and that heat powers weather systems such as hurricanes, storms, and monsoons. To observe the planet from an even broader perspective, scientists rely on satellites orbiting high above Earth. More than 50 dedicated weather satellites constantly monitor the atmosphere. Some remain fixed over the same location in space, known as geostationary orbit, allowing them to watch entire hemispheres continuously. Others move in polar orbits circling the planet from north to south and scanning every part of Earth's surface. These satellites track cloud formations, measure ocean temperatures, observe storms forming over warm waters, and even detect lightning flashes within thunderclouds. All of this information, from balloons, satellites, ships, floats, and ground stations, would be useless without the ability to combine and analyze it. That responsibility falls to powerful supercomputers located at major weather centers around the world, including the European Center for Medium-Range Weather Forecasts and the National Oceanic and Atmospheric Administration. These facilities run some of the most advanced computational models ever developed. Their computers divide the atmosphere into millions of three-dimensional sections and simulate how heat, moisture, wind, and pressure move between them over time. This process, called numerical weather modeling, attempts to recreate the behavior of the entire atmosphere and predict how it will evolve. However, forecasting the atmosphere is incredibly complex. Small measurement errors can grow dramatically over time, a phenomenon known as the butterfly effect. To manage this uncertainty, meteorologists run many simulations at once, sometimes dozens or even hundreds. Each simulation starts with slightly different initial conditions, producing multiple possible futures. When many simulations produce similar results, confidence in the forecast increases. When the results vary widely, forecasters know the prediction is less certain. One of the most remarkable aspects of weather forecasting is the level of international cooperation required. Because weather systems move freely across national borders, accurate forecasting depends on countries sharing data. This exchange is coordinated by the World Meteorological Organization, which facilitates collaboration between nearly 200 national meteorological services. Observations collected in one country can improve forecasts for another thousands of kilometers away. Even nations that disagree politically often share meteorological data because better forecasts benefit everyone. Billions of people depend on this system every day. Airlines rely on forecasts to avoid turbulence and dangerous storms. Farmers use weather predictions to decide when to plant or harvest crops. Shipping companies adjust routes to avoid severe weather at sea. Energy providers predict wind patterns to manage power grids. Emergency agencies rely on forecasts to warn communities about approaching hurricanes or floods. During disasters such as Hurricane Katrina, early warnings allowed millions of people to evacuate before the storm arrived, reducing what could have been an even greater tragedy. Weather forecasting continues to evolve rapidly. Artificial intelligence is beginning to analyze vast climate datasets and identify patterns that traditional models may overlook. New satellites with advanced sensors are being launched to measure atmospheric gases, ocean currents, and changes in Earth's energy balance. Researchers are exploring the use of drones and autonomous ships to collect data from remote areas where traditional instruments cannot operate. In the future, weather forecasts may become far more precise than they are today. Instead of predicting conditions for an entire city, forecasting systems might provide hyperlocal predictions, telling you that rain will begin on your specific street in a matter of minutes. Achieving that level of accuracy will require even more data, faster computers, and continued international cooperation. Despite its complexity, this global system operates quietly in the background of everyday life. Every time someone checks a weather app and sees a small icon predicting rain tomorrow, they are seeing the result of an extraordinary collaboration. Weather balloons rising silently into the sky, robotic floats drifting through the deep ocean, satellites scanning clouds from space, and supercomputers simulating the atmosphere, air all working together across nearly every nation on Earth. It is an invisible network spanning the entire planet, constantly watching the atmosphere and calculating the future. And every day, it tries to answer the same timeless question: what will the sky do next?